Welcome to Engineering Simple. So in this video, I'll continue talking about calculating the line to ground faults on a low voltage side of a transformer, basically in a power system, and then calculating the currents that will flow through the high voltage windings, low voltage windings, and the delta winding, tertiary. The first video I talked about kind of objectives of this video series. Then the second, and then I kind of set up kind of the system three-phase. Then we realized three-phase is kind of messy and it's hard to deal with. Then I said, okay, let's just draw, since we're dealing with steady state, let's just do one line instead of three-phase. Then the second video, I kind of drew the sequence networks. Then I got just a simplified, basically using the equivalent sequence impedances. Then I started kind of writing the equations for the equivalent impedances. So I would recommend going back to the previous videos. So now in this video, basically we'll go through and calculate the current. So now if I go back here, so if you see this current, the current that flows through the tertiary or Y side, so this current here, I'm going to use current division. So this current I0Y is equal to I0X times basically the impedance through the high side, the system A plus the high side divided by the sum of those two plus this zero sequence impedance of the Y. So I'm going to use current division basically. So I0Y is equal to the zero sequence impedance of the high side plus the zero sequence of system A divided by the sum basically of the two plus the zero sequence impedance of the Y times, because basically the entire thing, times I0X. So again, I'll go back here. So you can see it's kind of, that's what I'm doing here. So this current here is equal to the sum of these two impedances divided by the sum of the two impedances plus this impedance times this current here. So that's what I'm doing. So I know this quantity here, that, but I don't know I0X. So I have to calculate it. So, and again, you would have to go back to the diagrams to understand how to calculate it. So if I go back, so here, basically before entering A, so you have I0. So I0 here. So I0X is equal to this impedance here divided by this impedance plus the equivalent of these impedances here. So times I0. So all I'm doing here is current division. So system B divided by system B plus system A plus the zero sequence of H, which is in parallel of zero sequence of Y, plus zero sequence of X. So basically you have two impedances. So you have this and you have the equivalent. This entire thing times I0. So basically you have basically what I'm doing, you have this impedance, you have the equivalent impedance here. You kind of take the equivalent of this impedance. You take this impedance plus that impedance in parallel with this impedance here. Once you get that, plus this. So from current division, current division, if you have, so basically, yeah, so all I'm doing here is current division. So now, but again, so I know all these impedances, but I don't know this zero sequence current. And I know I0 is equal to I1, the positive sequence current is equal to the negative sequence current, which is equal to the voltage divided by the positive sequence impedance plus the negative sequence impedance divided by the zero sequence equivalent impedance. So yeah, so if you go back here, you will see that, yeah. So this I0, so because it flows in the, so this is I0, so it flows through here, so this is still I0, and also it's I2, so it flows through here, and this is the positive sequence, so I1 is equal to I2, which is equal to I0. So that's what I'm doing here. So I know this voltage, again, we said it's going to be 1.05 per unit, and I know this, I know that, so I can calculate I0, and once I calculate I0, I'll plug here, then I'll get I0x, then I'll plug that here, and I'll get I0, the current through the tertiary. Then I get all the currents. So now, if you go back to the diagram, the positive sequence current through H is the same as the positive sequence current through the X or low voltage, which is equal to the positive sequence impedance of system B divided by basically the sum system B plus positive sequence current of system A plus the positive sequence current of the transformer times the positive sequence current, which we obtained from the previous slide. So really all I'm doing here is I'm doing current division. So because I0 or I1, I2 basically will flow. So I'm just doing, basically I'm taking this, the equivalent, this impedance is in parallel with this impedance, so I'm doing current division. So this I1H is equal to this impedance divided by the sum of these impedances and this impedance times I1. That's all I'm doing here. And you can do the same thing to the negative sequence impedance flowing through the high voltage, which will be equal to the same as the low voltage. So if you go back to the diagram, it will be obvious that it's just the negative sequence impedance through system B divided by that impedance plus negative sequence impedance through system A plus the negative sequence of transformer times I2, or the negative sequence current. So if you go back to the diagram, it will be obvious. So for I0H, or the zero sequence current flowing through the high voltage winding, so basically I'm still doing current division. Zero sequence through the Y divided by zero sequence through the Y winding plus system A plus zero sequence of H entire thing times I0X. And I already calculated I0X here, so you can just substitute. So basically so if you come back to this diagram, I0H is here. So you have these impedances, the sum of them in parallel with this impedance. So this current here flowing through the high voltage is this impedance divided by the sum of these two impedances and this impedance times I0X. So it's just current division. Again, I0X I calculated from the previous slide. So I'll stop here and I'll continue on the next video. Thank you for watching.